Alright, we are back to type classes, and armed with a new tool in the form of type enrichments, we're finally ready to show what type classes are truly capable of. Alright, so let's get back to our IDE and to the type classes application, and looking at this code, I found that we have quite a bunch of mixed code, so let's sort this out. Let's move the equality stuff into a new Scala class in the exercises package, so let's name this equality playground, and let's move these guys here, and let's also move the user, or at least copy it or import it. Might as well import it. Okay, then let's move our little companion object for equal and our little test here. Okay, and let's also copy John over. Okay, and let's also move our type class template to a new file. The IDE should be smart enough to allow me to go to the part for implicits and just paste the code here. So if I just paste the code, the IDE created the my class template Scala file with the trait and the companion object, which will leave us with our little type classes application with our HTML serializer and our little imaginary social network. Let's also copy this comment to the equality playground because this is where it makes sense, the ad hoc polymorphism. And let's get back to type classes because that's where I want to focus. Cool, so we're back to our HTML serializers, and this will be part 3. So we know about type enrichments from the previous video. Now, in the context of type classes, type enrichments will allow us to invoke our little type class pattern for any type for which we have an HTML serializer. Let me give an example. So let's create an implicit class, which will be a wrapper over a value. Let's call this HTML enrichment with a value of some type, which warrants the need for a type parameter here. And let's add a method called toHTML. And this will need a serializer, which is of type HTML serializer for t, and this will return a string. And the implementation here is going to be serializer.serialize with the value. So let me show you how this would be useful. If I print line john.toHTML with a user serializer, then this would be a valid call. I would say, please serialize John using this user serializer, and I can pass in some other serializer if I want. So if I run this, if you remember, I'm going to get this little div. So as you see here, we get the same div with this little call because the toHTML method is implicit because John was wrapped into an HTML enrichment for user. Again, this is rewritten by the compiler as println new HTML enrichment for user with John as the value inside .toHTML with user serializer. That's because the toHTML method does not exist for the user class, so the compiler tries wrapping John into whatever implicit has the toHTML method that takes a user serializer. Now I can go even a step further. Let's say this toHTML method also has an implicit parameter. So if I have an implicit parameter, of course I can use it explicitly, but I can also use it implicitly, having defined an implicit user serializer. If you remember from the previous video, we had the user serializer made implicit. So if it's implicit, then I may freely omitted here in the toHTML call. So I can simply say john.toHTML, and the compiler will inject the user serializer as the parameter because it's an implicit parameter. So notice that we're left with this simple call, john.toHTML, as if it were built into the user class. So this is very cool. This is super expressive, and it also solves our early problems because of the following reasons. We can extend the functionality to new types, because this HTML enrichment thing can wrap any type. So if we have, for example, this int serializer that we made implicit earlier, we can also say, without any further addition, to.toHTML. Because we can convert to an HTML enrichment of int, and we also have an implicit serializer for int. So if I simply run this, I'm also going to see this little div style color blue with the value 2. So we can super easily extend this to new types. We can also have different implementations for the same type. So remember earlier with polymorphism, with normal polymorphism, that we either lose type safety or we're stuck with one implementation for serializing something to HTML. But here we can choose implementation, either by importing the implicit serializer into the local scope or passing it explicitly. So if I say, for example, print line john.toHTML with partial user serializer, then I can simply use that. So if I run this, I'm just going to see John's name. So notice how flexible this is. And as a bonus, which I think is also very cool, this is super expressive. So the type class pattern here now composes of several parts. First of all is the type class itself with all the functionality that you want to expose. For example, here in our HTML serializer, this is our type class, and this is our functionality that we want to expose. So the type class itself, then the type class instances, some of which are implicit. For example, this user serializer or the int serializer. All right. So the type class instances, and then conversion with implicit classes that will later allow you to use your type class instances as implicit parameters. So these are the main elements of enhancing your type with a type class. So our type class here is HTML serializer with type T with all those methods inside. The type class instances are user serializer, int serializer, and all other serializers for all the other types that you want to support. And conversion with implicit classes is our HTML enrichment. So I'll mark these down. Now let's see this in practice. Let's go to the equality playground and let's do another exercise. Let's improve our equal type class with an implicit conversion class. So improve the equal type class with an implicit conversion class. So the same thing that we did for HTML serializer with the HTML enrichment thing, I want you to do the same for the equal type class. And this implicit conversion class will have two methods. One is called equals equals equals, which will take another value of type T, or of type whatever you want, right? I just named it T. And this will invoke the equal type class to the value this implicit conversion class will contain and the other value that is taken as a parameter here. And I also want you to implement the opposite, the not equals. This will just return the opposite of this guy. So this will also get another value of type T. Let's also name this appropriately. And this will also invoke the equal type class for the value contained in this implicit conversion class and the parameter. So pause the video now and do this exercise yourself. This is important, all right? This exercise is not so much a challenge in writing code as it is a test in your understanding of type classes, all right? If you've understood type classes so far, in 2 lines you should be done. But if all this type class magic and implicit conversions and all this kind of stuff are too heavy for you right now, or if it all feels a blur, don't worry, this is normal. We're doing an advanced course, all right? So things are supposed to be hard because otherwise everyone would do it, okay? But I do want you to take the time to really understand implicits and type classes before attempting this exercise, okay? Don't jump to the solution until you're either done or out of ideas. And if you get stuck, feel free to ask. So pause the video now and I'll come back with a solution in just a few seconds. Alright, so I hope you did that. Because the solution should be fairly straightforward. This will follow the example with the HTML enrichment that we wrote earlier. So I'm just going to write an implicit conversion class, and I'm going to call this typeSafeEqual. I'm going to parameterize that with a type, and I'm going to wrap that with a value of type t. All right, and this will contain the 2 methods. Let's start with one of them, let the equals, and this will receive another value as a parameter, so other of type t, and as another parameter list, it will receive an implicit equalizer, which is of type equal t. And this will return a Boolean, and the implementation is going to be equalizer.equal, or apply, between value and other. And that should be it. And the not equal should be almost identical, but it will just return the opposite. So now that we wrote that, here's what we will be able to write. As a test here, we can say John, the user, and equals another John. So a lot of magic happens so that the compiler can compile this expression. And if I go ahead and run this, but of course I can't because this equality playground doesn't extend app yet. So let's make it extend app. So if I run this, I should be seeing true. So see? It's true because, and here are the steps that the compiler does for us so that it can later print true at the runtime. First, it rewrites this expression as John dot equals another John, because it will interpret that as an infix method. Well, is there a triple equals method on user? Well, no. So it will try wrapping the user with something that has the equals method. Well, it just so happens that we wrote a typeSafeEqual implicit class, which is a wrapper over any value of type t, which also is a valid match for a user. So the compiler will wrap that into a new typeSafeEqual instance of user with John as the value inside, and it will call the equals method on that, another John. Okay, then the compiler will say, okay, this method here also takes an implicit equalizer. Well, do we have an equal user implicit value so that we can pass in here? Well, we do, as an implicit object, name equality. This extends the equal user type class. So the compiler will then rewrite that into another John and name equalizer, or name equality that we called it. So this is the complete expression that the compiler rewrites our little equality method to. But notice that this is so much more expressive and reminiscent of JavaScript with this triple equal sign, which brings me to the main advantage of this typeSafeEqual thing, which, as the name suggests, it's type safe. What does that mean? Well, if I try to print line John equals 43, I can write this expression because I can compare any two references, but of course this will return false because these are unrelated types. But if I try to print line John triple equals 43, then this thing will not compile. So basically, if I use this triple equals sign, the compiler will force me that the two operands here must be of the same type. So that's why this thing is type safe. The compiler prevents me from even compiling the code. So this is massive improvement in our code. All right, let's get back to our HTML serializer because I want to show you a couple more things. First, I want to talk about context bounds, which is a new thing. So let's say in our little backend code, which generates a whole bunch of HTML, that we have a small utility method called, let's say, HTML boilerplate of type T, right? And we put in some content of type T and an implicit serializer, which is an HTML serializer of type T, because we now know how to work with type classes. And this will return a string. And let's say this HTML boilerplate code returns something like an HTML body. Let's say we return an HTML body and the content.html or to.html. And let's also pass in the serializer here. Okay, because we want to use serializer explicitly in the method implementation. And let's also close our imaginary HTML tags like /body/HTML. Now, given this HTML boilerplate, which has quite a hefty method signature, I can write that in a sweeter way in the following way. So I can name this HTML sugar, and here is what I'm about to write. Notice this. I'm writing T:\HTML serializer. And this receives just the content, which is of type T. And this will receive a string, this will return a string, and the implementation is just going to be identical, except that I can't use serializer because, and here's the context bound thing. This is a context bound, which is telling the compiler to inject here an implicit parameter of type HTML serializer of type T. The advantage is the super compact method signature. See, this is super readable. But the disadvantage here is that we cannot use serializer by name because the compiler injects it for us. Which brings me to the final thing that I wanted to show you, which is implicitly. Implicitly is a method. A very cute method. Let's create a small example. Say in our little social network we have some data privacy things and we have permissioning on our various things that we show on the page. So let's create a small case class called permissions, which has, let's say, a mask of type string. So this is created in some part of the code in the huge code base of our little social network, and somebody in our team implemented an implicit val. Let's call this default permissions, which is of type permissions, and the value here is permissions with say 0744, which is the Linux kind of permissioning for lack of a better example. But somebody created default permissions of type permissions in some other part of the code. And we, in some other part of the code, we want to surface out what is the implicit value for permissions. And for that, we could say val, let's say standard perms equals, and the method is implicitly of type permissions. So notice that we use implicit values mostly as implicit parameters into methods, and we only use their APIs inside those methods. But if we do need them in some other part of the code, it makes sense to want to surface them out, and the implicitly method does exactly that. Now, if you have a few seconds to spare, I would encourage you to sit and think for a couple of seconds of how you would super easily implement an implicitly method. If you're really curious, you can command-click here or control-click and see how the implicitly method is implemented. You would be surprised of how simple this is. And as another use case, going back to our HTML sugar method, if we want to use our serializer inside, we can say val serializer equals implicitly HTML serializer of type T, and then use the API of the serializer as you see fit. And you can also pass it explicitly here. So this is basically the best of both worlds. You have both the super compact method signature, and you can also use serializer by name, right? So kind of like having the cake and eating it too. All right, we've come a long way, so let's recap what we've learned. We've learned about the type class pattern in this multi-part lesson. So this starts with defining a type class, which is nothing but a trait which takes a type parameter and just defines some operations. Now, the second step is creating the type class instances which implement those operations for a specific type. Those instances are often implicit. Then we have two options going forward. Now, one is to surface out the type class instances by creating a companion and writing an apply method, which will allow us to use a type class instance without us knowing that it's there. Option 2 is to go even further and do a pimp my library style enrichment of a type and add a special method that also adds an implicit type class instance as a parameter and uses that, which then allows us to simply call that method on our enriched types as if it were built in. I personally like this one. This was a hard lesson, and I want to congratulate you for following through. I want to tell you that you are already ahead of most, 90% of Scala programmers, because very few people really understand implicits and type classes. Now, let's solidify our practice in the next video through yet another example of a super tiny library based on type classes. So I'm waiting for you there.